Before I start my talk today, I would like to ask the participants if they have any questions on yesterday's talk. They can raise hands and we can discuss first for 5 minutes or so. Then I can actually start. So please raise your hands in the Zoom. Okay, I don't see any hands here in the Zoom menu. So let me start. So yesterday we were discussing the central engines of AGN and what powers the huge luminosity we observed from AGNs. And I basically mentioned that this is the AGNs are essentially powered by accretion of material onto a supermassive black hole. And this particular information we derived or we inferred from these observations of large luminosity. And if we use the Eddington limit arguments, the large luminosity essentially lead to large mass, and which must be confined into a very tiny, a very small region, and that which we inferred from Riffitt time variability. So this essentially tells us that the AGNs are essentially compact object, and the mass is huge, and the size is small, and that's why they must be black holes, supermassive black holes. And there are this is just an estimate of mass, but there are other techniques to actually measure black hole masses in active galactic nuclei. We will not go into the details, but there are much more accurate techniques. And now we know that AGNs have the AGNs have supermassive black holes with a very accurate measurement of masses. I also mentioned some of the important parameters to remember for AGNs is that the masses of the central supermassive black holes can range from 10 to the power 5 to 10 to the power 10 solar mass or so. They are powered by accretion. Within the efficiency of this energy release from this accretion process is about 10%. Actually, it varies from something like 10 to 30% or so, depending on whether the black hole is spinning or not. Their size scale is comparable. You can compare with the size of the Schwarzschild radius. Of course, I'm talking about the black hole and the innermost regions. Of course, the emission from different bands can arise from far away region. Of course, we will see this X-ray emission actually arises from very close to the black hole, while the UV will be slightly further away, and optical emission even further away, the continuum emission. We will see some of these characteristics. And of course, the radio emission can arise from very close to the central black hole to all the way to parsec, kiloparsec, and even megaparsec scales. And the luminosity is typically of the order of the Eddington luminosity, which we also discussed in yesterday's talk. So if we talk about the Asian central engines, and as I mentioned, we observed optical spectra. Some of the AGNs have emission lines, of course. Some of them have broad emission lines, and as well as narrow emission lines. Some of them have only narrow emission lines. Some of them even do not show evidence for strong emission lines. So and in X-rays also we observe different characteristics, and many of the widely different observational properties can be explained in the AGN paradigm, and which essentially says that AGNs have more or less similar central engine, and the difference in observed property is basically due to our different lines of sight to the central engine. So the AGN central engine essentially consists of a supermassive black hole at the centers of an active galaxy, and this supermassive black hole may be spinning highly, or it may not be spinning. That's I mean, in many cases now we have observations that supermassive black holes are actually spinning at pretty highly, in fact. And this supermassive black hole is accreting material from the host galaxy, and the material which is being accreted cannot directly fall onto the black hole because the conservation of angular momentum. It forms an accretion disk around the supermassive black hole, and this accretion disk is source of the optical ultraviolet continuum emission, which is shown in the middle in the bottom center panel here in the blue shaded region. This is called the big blue bump emission, and we'll see in little more detail. Um, um, okay, but then we also have the X-ray emission at, of course, at higher energies, and this X-ray emission is thought to arise from something called hot corona, where the interaction between the disk photons and the hot corona gives rise to X-ray emission. That also we'll see in little more detail. And if you come to the longer wavelength side, in the infrared, we usually observe this kind of a bump kind of a emission, another component. And all these components you could clearly see in radio quiet agents and in radio loud agents, depending on the importance of jet emission, we may or may not see some of these components. For example, in blazars, everything will be swept out by the emission from the jet. So we will see more like and we will not see this component very observably many times. But there are, of course, in radio loud agents, we can see in some of the radio loud agents, we will see these components as well. Okay, so in the infrared band, we see this infrared bump component here. That is the infrared bump, and this component is thought to arise from this dusty torus, which is essentially in the form of a torus, and it is surrounding the supermassive black hole, the accretion disk, the disk, etc. And this does how does it produce? Essentially, the accretion disk and the hot corona are emitting. The accretion disk is emitting the optical ultraviolet photons, and this corona is emitting X's. All of them are actually illuminating this dusty torus, and that is absorbing some of this primary continuum in UV and optical from the central region, and reprocess, because its temperature is very low. It reprocess that emission into this infrared and gives rise to this kind of an infrared bump. So that explains the continuum component from infrared and let's say the optical UV and X-rays. This is the spectral energy distribution, typically spectral energy distribution of radio quiet agents. And in radio loud agents, of course, there will be a jet component, which is not shown here. Okay, and how do we understand the line emission which we see in the optical ultraviolet? So we think there are two kinds of clouds which are giving rise to this the line emission, like this HL5s, beta, etc., from agents. So the one kind of clouds are called the broad line region clouds, which are closer to the accretion disk, closer to the central engine, primary central engine consisting of this supermassive black hole and the accretion disk. Because they are closer, they are, and under the gravity of the supermassive black hole, they are moving with high speeds around this black hole. So what happens? The emission from the accretion disk, particularly the inner accretion disk, which is emitting ionizing photons in the ultraviolet and extreme ultraviolet band, and these photons essentially ionize these clouds, the broadline region clouds, and after ionization, as a result of recombination and downward transitions, these clouds give rise to different kind of line emission, which we are observing in HL as Balmer lines and carbon, magnesium, to all these lines, oxygen, okay, not oxygen 3 here. So these broad emission lines are actually arising from what we see here, these broad components. This is I'm showing only the optical band. So this H beta line is arising from this broad line region. And similarly, we will see the carbon 4, magnesium 2, even carbon 3. Those lines also arise from this broad line region, which is closer to the central supermassive black hole. When and these lines, okay, then there are another set of clouds which are further away, in fact almost at the outside of this dusty torus, and these are called narrow line region. And the again, because of the same process, they give rise to line emission, but this time because they are much further away, their speeds of their velocity around the supermassive black hole is much smaller, and therefore these lines from the narrow line region appear to be much narrower. So then what happens in type 2 agents? We think that our line of sight is actually passing through this cold dusty torus. So therefore, because this actually obscures the entire central engine, which consists of the emission from this hot corona, X-rays, the accretion disk, even the broadline region clouds. And that is the reason, because this emission from the broadline region clouds are actually obscured, and therefore we do not see these broad emission lines. And the accretion disk emission is also obscured, so that is why we do not see very strong continuum in type 2 agents. While in type 2 agents, our line of sight is something like this, and so that it does not directly pass through this dusty torus, but it and therefore we have a direct view of this central engine. That is, we can observe the direct emission from the accretion disk, from the broadline region, as well as from the narrow line region. And therefore, we see broad emission lines, narrow emission lines, and strong continuum from accretion disk. There are some other kinds of AGNs which are not going to, but these are the basic difference between the type 1 and type 2 AGNs here. What about the innermost central engine? How much we understand about this? So this of course, we know that there are supermassive black holes, and there is also an accretion disk. But many of these things are not very clear, particularly the geometry of the innermost accretion disk, as well as the hot corona, which is giving rise to this X-rays. That is not very clear to us. We think that there are. We think the data are even today's data are consistent with different kind of geometries. One possibility is that we have the central supermassive black hole around this. This is accretion disk. Accretion disk may be extending to very close to the black hole, where the generality allows stable orbits, so-called the innermost stable circular orbits, which would be for a non-spinning black hole, which is 6 times the gravitational radius, and for a maximally spinning black hole, it is 1 gravitational radius. So the accretion disk can extend up to that radius. In some objects, it may not be. You may not go down to this innermost stable circular orbit, but it can actually truncate at even at larger radii, maybe 50 RG, 100 RG. These things are possible. But the another thing is that the hot corona is probably in something like this, which again surrounds this, which is in the innermost region, and surrounds this black hole, and even surrounds the innermost accretion disk. So in another picture, the another possibility is that we have in the bottom panel here. These are all schematic pictures. These are not observations. In this entire slide, all of these are schematic pictures. So in the bottom right panel, another possibility is that we have this accretion disk around the central supermassive black hole. But in this case, hot corona is very compact at a certain height above this black hole and along the symmetric axis of the accretion disk. and uh, and this is part of, in this case, the hot corona is actually part of the jet which gives rise to the radio emission, even in some cases infrared, optical, ultraviolet, even to soft X-rays or so. So the base of this jet is essentially acts like a hot corona, and that gives rise to the X-ray radiation. That is another possible picture. And of course, then I had discussed this torus and the broadline regions, etc. But the innermost center, in the central region, the black hole, the hot corona and accretion, these two are the kind of possible geometries we think is operating in any in some of the AGNs. So if we want to probe the innermost regions, then we will need to use appropriate band, which the emission from in which is arises from very close to black hole. And how do we know which band or which emission, whether it is optical, ultraviolet, radio, or X-rays, is actually arising from very close to black hole? That, as I had mentioned earlier, we can infer from the time variability of these emission, and depending on the size scale it implies, we can infer that the emission from a particular band must be arising at certain from certain region. In case of X-rays, I had mentioned that we have a doubling time scale of about 1 hour or so, even shorter sometimes, depending on the black hole mass. And that tells us that the size scale for the emission region is very, very compact, comparable to the size, comparable to the celestial radius. So because of this reason, we think that X-rays are actually arising from the immediate environment of supermassive black holes. So therefore, if you want to probe the innermost regions around supermassive black hole, then we need to use X-ray emission from these agents. And if you think of X-ray radiation, how does the spectrum, X-ray spectrum, look like? So here I'm showing some of the simplest X-ray spectrum, so that to highlight the main spectral component. So let's focus on the right side panel, which shows the X-ray spectrum of two agents. One is this PG1416 -129, and another one is NGC4151. Let's look at the X-ray spectrum of PG1416 -129 in the red color here. And if you see the axis is here, this is the photon flux. This is the photon number flux, plotted as a function of energy, and both are in a log scale. And in such a plot, in this when we are plotting in log scale, a linear line is like a power law in linear scale. So if you see this X-ray spectrum, the red line, this looks like approximately linear relation here. So that means that X-ray radiation is essentially dominated by power law component. Okay, and there are some departures, of course, and there can be many departures which I'm not showing here. So first of all, below about a few kV, below about 2 kV, there is an excess emission that we call it soft X-ray excess emission. While at high energies, above about 100 kV or so, if the spectrum, the power line spectrum, does not seem to continue to very high energies. Rather, it breaks at few hundred kV. So there is a spectral break at few hundred kV. So these are the kind of signatures. Here, other features we will see later on. So now, if you look at the spectrum of NGC 4151, which is kind of similar, particularly above a few kV and all the way down to few hundred kV. It is again dominated by power line in this band, and then it kind of cuts off at few hundred kV. But there are differences in the low energy band, below about few kV. The spectrum, X-ray spectrum from NGC 4151 it kind of cuts off, and this is essentially due to X-ray absorption, because X-rays, the soft X-rays, where photoelectric absorption cross sections are high, the heavy atoms like carbon, etc., all the way to iron, they actually absorb these X-rays via the photoelectric effect, and therefore this X-ray radiation reduces. So it depends whether we have some kind of absorbing material along the line of sight, maybe in the host galaxy, maybe very close to the AGNs, or even in our own galaxy, depending on the obscuration column, the soft X-ray spectrum uh, may, 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 may may not be observable because of this absorption. So otherwise, these two spectrum are very similar, except in one case the absorption is high, therefore we don't see um, the soft X-ray emission from NGC 4151. Okay. But the thing to remember, this X-ray emission, the broadband X-ray emission from about zero point 0.1 to all the way few hundred kV is dominated by a power law continuum, and with a high energy cutoff at 100 kV. And this particular component is thought to arise due to quantization in a hot corona. So to we'll come back to the processes generating X-ray emission, but to look at more clearly the different emission components in AGNs. I have shown here the spectral energy distribution of AGN. This is for radio quiet AGNs, and of course for radio loud AGNs as well. First of all, if you look at in the optical ultraviolet band, we have this component shown in blue dash dotted curve is the big blue bump component. Okay, so this is the optical UV continuum we observe, and it looks like this. Okay, and if you go to the X-ray band here, okay, the big blue bump component actually can extend to almost at the softest X-rays, and this because of the absorption in our galaxy, extinction in our galaxy, we don't observe some of these emission, particularly at the extreme ultraviolet emission. We do not observe directly. Okay, but when you go to the X-rays, the soft X-ray and hard X-ray band, as I was mentioning, and this entire band is dominated by power law continuum. Again, here this plot is the flux in log units and frequency in log units. So it's again log units. Any linear kind of component is a power law, and here the hard X-ray is dominated by the power law, which is shown in light blue color. So that is, and then of course there are other components, and we will see there is a line emission at around 6.4 kV, that is due to iron kalpa, and we will see the origin. How does it originate? Then we have this bump kind of emission, which we call reflection hump, and we will see the origin from very basic physics. Then there is another component called the soft X-ray excess component, and we do not clearly understand the origin, but we have some models to explain this component. This is about the optical ultraviolet, the soft X-ray, and hard X-ray component, and this much is thought to be the primary continuum emission, or primary emission from AGN, that is from the accretion disk and hot corona. The other part, particularly in this infrared bump from radio quiet AGNs, so that again is a reprocessed emission from the dusty torus, as I had mentioned earlier. And when you come to the radio part in the radio quiet AGNs, the radio emission is very weak, but the objects are not radio silent. Even in radio quiet AGNs, we do observe radio emission, and sometimes jet structures also, but confined to only the innermost regions. In radio loud AGNs, the radio emission is very strong, and you know that how the radio morphology looks like for for few of the radio loud AGNs with Cygnus A, for example, I had mentioned to you. So here we will focus mostly on the primary emission. That means we will mostly focus on the central engine accretion disk and in the hot corona and the interaction between them. So first of all, this big blue bump component in the optical UV, that is thought to arise from the accretion disk. So because the supermass, the main process that is giving rise to the Asian luminosities, high luminosities, that is due to the accretion process. And this accretion process is in this accretion process, essentially the central supermassive black hole is accreting material from the host galaxy. And any material in the host galaxy will have some angular momentum. And because the angular momentum must be conserved, and because of that reason, the material being accreted cannot directly move in the radial direction and fall onto the black hole. What it does, it actually orbits, it around circulates around the supermassive black hole, and it forms an accretion disk, which is geometrically thin and optically thick. So, due to certain processes, when there is a gradual loss of angular momentum, so then the material in the accretion disk, it will gradually spiral in and finally disappear onto the black hole. And because it is optically thick, we can essentially approximate the emission from this accretion disk as a black body. But however, the standard disk theory shows us that the temperature is not uniform across the accretion disk, but rather it increases inward. In the innermost region, the temperature is higher, but in the outer region, the temperature is much lower. And this variation of temperature as a function of radius is given by this r radius to the power minus 3/4. Okay, so that's the dependence of the temperature on the radius. So in the innermost regions, for let's say for about 10 to power 7 solar mass black hole or so, the temperature is few Kelvin. So that means about 10 to power 5 Kelvin, 10 to a few electron volt. So few electron volt essentially translates to about 10 to the power 5 Kelvin. If you are talking about 10 to the power 6 solar mass black hole, it will be more like 10 or 20 electron volt. While for more massive black holes, it will be even lower. So in order to approximate or in order to find the emission spectrum of from accretion disk, what one simply does is divide the accretion disk in large number of rings and assume that each ring has a constant temperature according to this formula r to the power minus 3/4. And from each ring, then you take the black body emission at that temperature, take the area of that one, and that will give the strength of this black body, and you sum the black bodies from all these rings, and that sum is essentially the total accretion disk spectrum, which it looks like this. In the intermediate region of this spectrum, maybe in the optical ultraviolet band, you see this looks like more like a power law, because again in the log plot it looks like there's linear. So that this power law is essentially nu to the power 1/3. And of course, there is a wind tail at a high temperature because of the highest temperature in the innermost accretion disk, and religions image spectrum at a much longer wavelength. Okay, so that's the typical accretion disk spectrum theoretically predicted. Of course, this does not account for general relativity and all that, but this is the simplest thing one can actually do in little bit of time. Now, this spectrum, once we understand the accretion disk emission, and when we compare with the observations, of course, the agents emit in various different band, and just the accretion disk emission, which is confined in the optical ultraviolet band, cannot even explain the X-ray emission. So, how does the X-ray emission arises? So here we have seen this accretion disk is essentially gives rise to the continuum emission in the optical ultraviolet. Then we think that the innermost region essentially has two phases. One is this cold phase, which is the accretion disk with a temperature of a few tens of electron volt depending on the mass, and there is another hotter phase, which we call as the hot corona. And temperature of this hot corona is about 100 kilo electron volt in energy units. And this is optically thin, while the accretion disk is optically thick. So then what happens because there are in the hot corona essentially it consists of energetic electrons, while the accretion disk is emitting photons in the optical ultraviolet band. And these photons then interact with the highly energetic electrons in the hot corona, and they get inverse Compton scattered. And because this hot corona is more like a cloud, there are of course a huge number of electrons in this hot corona. So these photons can get scattered from one electron, then they get scattered from another electron. So, therefore, they have this repeated inverse Compton scattering. And in each inverse Compton scattering, there is a certain amount of energy transfer, and thus in the repeated inverse Compton scattering, there is photons, the original UV optical UV photons can gain energy, and they can actually become X-ray photons, and that is how this Comptonization or the repeated inverse Compton scattering process is generating X-ray photons here. But how does it give rise to the Paula component with a cutoff? That's the dominant X-ray spectral components in AGNs. To understand again through basic physics, let's assume, okay, we have this two-phase model. So what then happens that let's say this optical depth of this hot corona is tau, and observationally when we model the X-ray spectrum through this kind of composite spectrum, we infer that this is optically thin, as I had mentioned. That means the optical depth is less than about 1. So in this process, in the composition process, what happens? First, imagine that this accretion disk is, let's say, emitting like a black body, which is shown here in the red curve here. This is the spectrum log f nu versus log nu. And the red curve is the spectrum, let's say the initial spectrum from accretion disk. And the photons in this rising in this black body are essentially interacting with this hot corona. So in this composition process, what happens? You take the fraction tau, which is less than 1 of this black body component, so that its strength reduces, and this fraction is upscattered in a single scattering step by a factor 1 plus 4 kT by MEC square, where kT is the temperature of this hot corona, and MEC square, of course, the rest mass energy of the electron. So that factor is by that factor the spectrum here moves in one scattering step. So this black body moves to higher energy, but with reduced strength, because we have taken a fraction tau, which is less than about 1. And if you repeat this process for multiple inverse Compton scattering steps, then in each step the strength reduces, and the spectrum moves to higher energy. And if you have many inverse Compton scattering, the spectrum you will look like the black body component will with reduced strength and moving to higher energies will look like this. But when the temperature of the black body becomes kind of comparable to the temperature of the hot corona here, then there will be no more increase in the energy of these scattered photons. And at that point of time, because there is no more high energy photons, so the spectrum will break here. So now we have so many black bodies as a result of a number of inverse Compton scattering steps. And then when you add all these black bodies, it looks like a power law with a high energy cutoff. So and the high energy cutoff is comparable to the temperature of this hot corona. And that's how we produce a power law spectrum with a high energy cutoff in the composition process due to multiple repeated inverse Compton scattering of photons from accretion disk by the hot electrons in the corona. Okay. If you want to read more about this, these are the references I have added here. And we observe such a power law I have shown, we observe clearly, but now with this NASA mission called New Star, which is sensitive in the hard X-rays, up to about 80 kilo electron volt or so. So using the observations from this satellite, we can actually measure the high energy cutoff very clearly. For example, these are the observations from IC4329A, and this is the ratio of the observed spectrum and a power law, simple power law model. And because the model doesn't have a cutoff, so therefore there is a deficit of emission above about 20 or 30 kV, and that is a direct signature of the high energy cutoff. And when we introduce a high energy cutoff, then the data and the models look very much consistent. And what from this cutoff, because we in measure said that this cutoff is the comparable to the temperature of the hot corona. So therefore, by measuring the cutoff, we can measure the temperature of the hot corona, and that turns out to be depending on the depending on the geometry, and of course it turns out to be about 60 kilo electron volt in these agents, and tau optical depth of about 0.7 or so. So that's how we measure the properties of this hot corona via X-ray spectral modeling. And when you okay, so when you look at the X-ray spectrum in little more detail, and here you will see different components. Again, this is the log plot, log of flux as a function of energy plot here. So and again here, if you look at roughly, it is constant here. That's a power law with a photon index of about 2. So in the soft X-ray band, here you see number of these absorption features. These are all absorption line. Again, this is a schematic picture, not a real spectrum. But this one shows there's a number of this absorption lines, and then there are some kind of absorption edges as well. How do these things arise? These things arise because there is some kind of an obscuring or absorbing cloud along the line of sight to the central engine. So what happens in the ADN central engine is, of course, emitting this X-ray power law component, and these X-ray power law component must pass through some of the absorbing cloud. And this absorbing cloud, of course, will have different elements, and due to the X-ray absorption processes through photoelectric absorption, some of the radiation will be absorbed, and depending on the ionization stages, etc., you will see a large number of this absorption lines as well as absorption edges. And I mean, when we looked at the optical spectrum, for example, we did see some of the emission lines, but those were not like this numerous in number. Here, these features here, it may look like to you that these are kind of a noisy thing, but not really. These are all this is a very high signal to noise data observed from using Chandra. Chandra is a NASA mission. Chandra's high resolution grating spectra for about 10 days or so. And this is a really high signal to noise data, and these are all observed the significant features, and you see here like huge number of absorption lines, and these are much more, many more compared to what the number of lines we see in the optical, or even in ultraviolet. So what is the reason for this huge number of absorption lines in the agents? The reason is one can understand from here. So this X-ray band from 0.2 to 10 kV essentially covers the K cell bands of carbon to iron. When we say K cell band, so for example, take the example of iron atom here. So to ionize a neutral iron, it takes about 7.1 kV. But if you ionize hydrogen-like iron, that means iron and ion with one electron. If you want to remove the last electron, that takes about 9.1 kV. So this last electron, of course, will be K cell electron. So that to remove that last K cell electron from hydrogen-like iron, it takes about 9.1 kV. And And if from the neutral iron, if there is a transition from L cell to K cell, that gives rise to 6.4 keV lines. So this energy between 6.4 to 9.1 keV involves the K cell, and that is why I say I'm mentioning that this when we say iron K cell, that is from 6.4 to 9.1. And when we say the iron K cell, that means because it has hydrogen like, helium like, and down to neutral iron. So iron has 26 atomic number. So those 25 ions, and for each of those ions, all the transitions involving K cell. So even just from iron, you have so many ions, and for each of the ion, you have so many transitions. And now imagine, of course, there are other elements, lighter elements, for which the K cell, when all falls in this X-ray band. And not only K cell bands and the corresponding different ions and their different transitions from numerous levels. The L cell bands are also L cell bands from of silicon to iron also fall in this X-ray band. So that is why so many ions for all these elements and the transitions involving, they cause huge number of transitions, and that is the reason why we see such a huge number of absorption lines. And good amount of atomic physics is actually used to understand some of these absorption features, and many times we discover new lines in astrophysics rather than in laboratories. So this feature here around 0.75 keV are here, this was observed only with the advent of Chandra and XMM Newton in with these things were launched in 1909 and around. Before that, we didn't even know, neither from laboratory or not from in astrophysics. These are called something called unresolved transition array, and arise due to the singly ionized iron atom, and that's how we discover transitions, and that we discover these absorption features and the transitions, and then people use atomic physics and astrophysics then helps even atomic physics due to these discoveries. And this is the effect of photolytic X-ray absorption. So if first of all, the X-ray spectrum, a power law of spectrum is depicted, written as e to the power minus gamma, the energy to the power this minus gamma, and gamma is called the photon index because we are writing the spectrum in photon flux units. A is just the normalization, and this factor e to the power minus sigma nh essentially accounts for X-ray absorption. Sigma is the effective cross section as a function of energy, which this sigma essentially varies as energy to the power minus 8 by 3. That means for the lower energies, the absorption cross section is high. Therefore, the attenuation of flux is high at softest X-rays. And of course, this NH with higher and higher NH, the attenuation will be more and more because e to the power minus this factor sigma times NH. NH is the absorption column. So so this power law spectrum. This is again schematic spectral model, you can say, and a power law model with a photon index of 2, and how it is affected with absorption due to by material by of different columns. For example, NH 10 to the power 21, much lower column, and this absorption is spectrum cuts off here. But with increasing NH, the spectrum cuts off at higher and higher energy, and NH is, if it is really high, about 10 to the power 24, you see the spectrum cuts off below 10 kV or so. So that is the effect of neutral. If the material is neutral, then we see this kind of X-ray absorption. Here you will see that there are no absorption lines. Only you see this absorption edges due to different elements. For example, at 7.1 kV, you will see the iron K cell edge. Here at 0.4 kV or so, it is the carbon edge or so. And then you will see around 0.8 kV or so the oxygen edges and other things. But we don't see the absorption lines like what we saw here. It also has this some of these absorption edges which are not very clearly seen because of the huge number of lines here. But how does this absorption lines appear? So if the absorption lines appear when the gas is ionized. So depending on the ionization parameter defined is the luminosity, X-ray luminosity divided by the density of the atoms here and R square. So this is the ionization parameter. This is kind of proportional to the ratio of photons, ionizing photons, and the number of atoms. It is in that kind of number. So therefore, for every atom, how many ionizing photons are there? It's that kind of a number. That's why it measures the level of ionization of the gas. For neutral and almost neutral like material, ionization parameter is very low. Then we see this absorption edges. But when you increase the level of ionization increases, and where that means the electrons from the neutral atom have been removed. So there are vacancies, higher excited state vacancies. So this means that the electrons can actually absorb energies, absorb X-ray photons, and move to excited levels, and that creates absorption lines. And that is why in the ionized material you see these absorption lines. And when this ionization parameter is very high, this log xi 4, that is this ionization parameter 10 to the power 4 or so, then the material is almost completely ionized. So therefore, you do not stop seeing any of these absorption features, neither the lines nor the absorption edges here. Okay, so we discussed this absorption characteristics. We have also discussed the power law, dominating power law, and now let's discuss this iron K alpha line and this reflection hump. Okay, so I'll skip that soft access part. But if you look at this K alpha line in observations, it looks something like this. This is the real data, and this is the ratio of data and continuum model. Without that continuum model, of course, does not include the model for the iron line, and this is done to show the shape of the iron line from an agent called MCG 52316. This we observed using XMM Newton and Suzaku later. So this is the same spectrum, but much better signal to noise observed with the XMM Newton, the European mission, and the Japanese mission, Suzaku. So what you see here is there a narrow iron K alpha line. Of course, it has certain width, but that is due to the instrumental width. We do not really resolve. And there is another peak. The main peak is the iron K alpha, and another peak that is iron K beta line. And then, in addition, if you remove these components, then there is a broad component like this. Okay, and if you look at the broad component and you measure the width of that, and that turns out to be about 50,000 kilometer per second. Okay, you will recall in yesterday I had mentioned that in the optical ultraviolet we observe this broad emission line with a typical width of about 5,000 kilometer per second. Now here we are observing line width of 50,000 kilometer per second. So this means that the line emitting material, that material which is giving rise to this iron K alpha line, iron lines, that is moving with much faster at much faster speeds compared to the material which is giving rise to the optical ultraviolet lines. And because of such high speeds, we think that this arises from very close to the black hole and from the accretion disk. In fact, so how, and this essentially constitutes one part of the reflection spectrum, X-ray reflection spectrum, and let's see how does that arise. First of all, as I had mentioned, we have this accretion disk and the hot corona. The accretion disk photons get in Bose-Compton scattered, and they produce this X-ray power law continuum. And this power law, of course, goes in all the directions, and some of them we observe also. But some part also illuminates this accretion back to this accretion disk. Okay, so now there is an interaction of this accretion disk material and X-ray photons. Earlier, we had seen the interaction between optical UV photons from the disk and energetic electrons in the hot corona. Now we are considering the interaction of X-ray photons, high energy photons, with the disk material. And as you mentioned, this disk has the temperature of the disk is few electron volt. That means maybe hydrogen is ionized, some helium may be ionized, but the heavier elements are not fully ionized. At least maybe the outer electrons are removed or something, but there are electrons bound to heavier electrons. So the disk you can consider it is a partially ionized material, and it is optically thick. So of course there may be some atmosphere, etc. But now we have to think of this interaction of X-ray photons with the elements with the bound electrons in them in this accretion disk. So first of all, there because there are some free electrons, so there will be the Compton scattering. This time it will be direct Compton scattering, and because in the low energy side it will be like Thomson scattering. So without any change in the energy, the X-ray photons will be scattered by free electrons in the disk. At high energies, there will be some energy reduction of this X-ray photons, and we will see that. And because the elements, the heavier elements in the accretion disk have bound electrons, and these electrons will absorb the incident X-ray photons and get ejected through this photoelectric absorption process, and then they will also generate the fluorescence line. For example, what can happen? Take this example of this iron atom. So in this particular case, when let's say when the X-rays above 7.1 kV illuminate such a material with iron atoms, then the K cell electron, because K cell electron will be ejected, because that is the most likely thing. So and then there will be a vacancy. In such a case, this ion is in excited state, and this L cell electron will jump to K cell, and a characteristic and these photons with the energy difference between this K and L cell will be emitted, and that is the K alpha photon, and that these transitions constitute this iron K alpha line, which we see here. So in this figure now, this is a simulated. This is generated from simulations. So what is assumed that the X-ray power law, this one without any cutoff or anything like that, is essentially illuminates a semi-infinite accretion disk, and then there are this interaction photolytic absorption, and followed by that this fluorescent the transition from L to K cell and generation of this iron K alpha line. Similarly, other elements like nickel, etc., will also give rise to this kind of lines, but they because their abundance is much lower, and for the lighter element the fluorescence yield is also very low, so we don't see the strong lines. The strongest line is the iron K alpha line. Okay, some of this continuum emission here is due to the Thomson scattering here by the electrons, and the combination of this photoelectric absorption and Compton scattering produces this kind of characteristic structure lines I already explained, and here you will see this kind of shape around 7.1 kV. This is due to this absorption due to this iron atom. That's due to the K cell electrons are being ejected due to absorption of photons above 7.1 kV, and the absorption cross section varies is energy to the power e to the power minus 8 by 3, and that dependence creates this kind of signature. Okay, and when you go to really high at very high energies, then due to the Compton recoil effect, the high energy photons actually lose their energy to the electrons in the disk, and they move to lower energies, and then this hump kind of structure because of this loss of energy of high energy photons and loss of energy due to this absorption due to iron K atom, that produces this hump kind of emission, and that is what we call is the reflection hump. And we do observe such things. But before I go to the reflection hump, as I mentioned, this is here the strongest line is this iron K alpha line, and because that is arising from in the innermost regions of the accretion disk, very close to the black hole, and where the speeds due to special relativity and gravity are strong, and that modifies the line emission. In the rest frame, of course, it will be like a delta function or so. But because even if you consider simple Newtonian physics, because the disk is rotating, one part is going away from us, and another part is moving towards us. So because of the Newtonian physics and rotation here, this line profile will look like this double horn kind of profile. And if you apply special relativity, and there will, due to the beaming effect, where the material which is coming to moving towards us, then and in this case, the emission which will be going in the 4 pi solid angle directions in the rest frame, but in the because of this motion towards us in the observer's frame, it will be beamed. It will be confined to a very narrow angle. That's the relativistic beaming, and because of the beaming, this part which is blue shifted becomes much stronger, and because of the same effect, because the from the other part where the material is moving away from us, and the beaming, therefore the radiation is beaming away from us, and there is a reduction in the strength. And due to the transverse Doppler effect, this entire thing is rate shifted due to the time dilation effect. And when you apply general relativity to the gravitational redshift, the line photons move to even lower energies. And when you sum all these effects, the final line profile looks something like this. And this in the right side, this was actually observation the discovery of such a broad iron line from one of the AGN MCG 63015, and how this relativistic model describes the data so well. And you see this double peak, double horn asymmetric line profile, like what we saw here, and blue peak, and possibility of this red peak, and large width of this line, which is all due to this relativistic effect. Once this was discovered, and then people studied many other lines, and because here this red wing is due to gravitational redshift here, and gravitational redshift will be higher if the disk extends closer to the black hole. And from general relativity, we know that if the black hole is not spinning, then the stable circular orbit is slightly further away at 6 times RG. While if it is maximally spinning, the accretion disk is very close. It is at 1 RG. So that means for maximally spinning black hole, the effect of gravitational redshift will be stronger. And therefore, the line which is shown here, line profile, which will be broader, and the line photons even observable to few keV. While in the case of Schwarzschild black hole or non-rotating black hole, the lines is actually narrower. And therefore, by measuring the strength of this red wing, strength and the extent of this red wing, one can measure black hole spin, and that is what has been used. This broad iron lines have been used to measure the black hole spin of some of these agents. I think my time is up, so I will stop here. I will skip some of these things just to mention this. This is the broad iron line measured from this MCG 63015 from much improved data, something like 325 kilosecond observation using this European mission XMM Newton. And you see clearly this K alpha narrow K alpha peak, K beta peak, and this broad emission lines even going down, even observable down to 3 kV or so. And here, this very broad iron line requires iron alpha emission from below 6 RG, and the inner radius of the accretion disk is estimated to be 2 RG, and the black hole is inferred to be highly spinning in this AGN. If you want to know more about AGNs, there are a number of books. The first and very simple book is An Introduction to Active Galactic Nuclei by Broadley M. Peterson. If you don't know about agents and you want to have a basic understanding, you can read this book. Then there are more advanced book, particularly talking about agent central legion is by Volker Backman and Chris Schrader. There's another very nice book came recently. That's the Physics and Evolution of Active Galactic Nuclei by Hagai Netzer. And when we discuss the central legion, I try to understand the central legion, vacuum disk, hot corona, general relativity, etc. These some of these things are also very much common in other compact objects like black hole X-ray binaries. You may have some talks on black hole X-ray binaries, even neutron star X-ray binaries. So this accretion process is very general among accreting objects, particularly particularly around supermassive black holes, stellar mass black holes, neutron stars, white dwarfs, etc. Even stars which are forming, there also accretion plays major role. And some of many of these things, particularly related to compact objects, white dwarf, neutron star, stellar and supermassive black holes. If you want to understand more about that, then this book by Longier, MS Longier on high energy astrophysics. This is a very nice book, and one can actually follow these textbooks. Here I will stop. Thank you very much. And if you have questions, I can take the questions. Please raise your hands. Okay, we have questions from Saurav Upare. So can you go ahead? Can you ask this question, Saurav? Uh, Saurav, can you unmute and ask the question? So okay, by that time we get the question. Here is a question in the Google Doc by Subhadip Datta. So she is saying in the literature, we find that relativistic electron positron jets are not possible. As I know, for truly relativistic jets, we need to have electron proton pairs are jets and AGNs are X-ray binaries, leptonic electron positron, or they may also be baryonic. So the current status of our knowledge is such that we do not have a very clear idea on the content of jet. And in case of, AGNs, where the one particular class, the Blazar type AGNs, so the jet emission over the entire electromagnetic waveband. In some of the blazars, the so-called BLEC type blazars, where people can actually model the entire spectrum with the jet content having only leptonics, so electron positron plasma in the jet can give rise to the observed spectrum in lake objects. Um, Even in the other types of blazars, so-called the flat spectrum radio quasars, because these blazars emit strong emission in gamma rays, which really requires highly energetic particles. There also, people can model the jets with the leptonic models, but sometimes one component is not sufficient. And that is kind of a drawback of this leptonic models. And there are people who have also used the baryonic models. So we, to be sure, we do not clearly know the content of the jet. In one case, not in AGNs, but an X-ray binary SS433. There, clearly, I think line emission has been observed from the jet, which is moving. This line emission is also to be observed, and there it is clearly not pure electron position plasma, but the jet contains this baryonic component there. So this much is the kind of evidence. I do not work extensively on the jets, but this is what I am aware at this moment. Okay, so Saurav, can you now ask? You can unmute and then ask the question.
Hello, sir. Good morning.
Yes. Good
Am I
morning.
audible?
Yes, you are audible.
Sir, as you mentioned, the hard X-rays are responsible for Compton scattering. I
Mhm.
have seen in the sir, as hard X-rays are of higher energy, so they are highly penetrating in any atom, and
Yes.
Compton scattering will be more prominent for the tightly bound electrons. Is it
So,
so?
so when I mentioned Compton scattering, the origin of hard X-ray emission is by repeated inverse Compton scattering by relativistic electrons.
Okay.
So in the Hot corona, we are requiring only relativistic electrons. Okay, those relative electrons, when we say highly energetic, I mean when the temperature is 100 kV or so, they are of course free electrons. Those electrons are inversely Compton scattering the optical EV photon from the disk. Therefore, transferring good fraction of their energy to the photons in repeated inverse Compton scattering. That is giving rise to the hard X-ray photons.
Okay, sir. Sir,
And even if you are considering the interaction between these photons and electrons bound in let's say atoms, and if the photons have high energy in direct Compton scattering, for example, so if photons have high energy, much higher energy compared to the ionization energy of these electrons, which is kind of a few tenths of electron volt, and while the photons, if they are in hard X-ray band of tens of kilo electron volt, then the whether the electron is ionized or not, it doesn't matter there, because the energy, photon energy, are much higher in direct Compton scattering.
okay. Sir, as OG electrons are also responsible.
OZ electrons you get from in the ionization process, of course. Responsible for what? Oh, so
Means
so OZ electrons there. Yes, so because there will be the electrons which are removed. The K alpha photons, which K alpha photon can be absorbed, and this OZ electrons can be emitted. Those electrons will be in the accretion disk, and those electrons will also play a role in Compton or Thomson scattering of incident X-rays from the corona. Yes.
that's